Welcome back to the Deep Dive, where we take a stack of your sources and really pull out the most important nuggets of knowledge for you.
Great to be diving in.
Today, we're tackling something pretty fascinating. The intersection of artificial intelligence and, well, safety. Specifically, how do you make AI incredibly smart and inherently safe when it's controlling real-world stuff?
Yeah, it's a classic problem. You want peak performance, but you absolutely cannot compromise on safety.
Exactly. That tension, push the limits, but guarantee safety.
Right, and a lot of AI learns through trial and error. That's fine in a simulation, maybe, but you try that directly on a power plant or self-driving car. That introduces some really fundamental safety issues.
Lead challenges.
Huge. But the source material we have today lays out a really elegant solution to this exact dilemma.
So our mission today is to unpack this really groundbreaking framework. It promises to sort of resolve that conflict. We're mainly drawing from a research paper, The Data-Driven Safeguard. Redefined Intelligent Control as Smart and Safe by Tanit Wonghong. It was presented at Econ 48. And we've also got some supporting bits on controller performance prediction and a key mathematical idea that makes it all tick.
Convolution, yeah. We'll get into that.
This is genuinely a shortcut to getting up to speed on something that's going to shape, the future of automation. So, okay, let's unpack this.
Let's do it.
So maybe first, what do we even mean by intelligent control? The paper points out, interestingly, that historically it's been kind of hard to nail down a precise definition or even measure intelligence in these systems.
That's very true. It often involves AI, sure, neural networks, fuzzy logic, machine learning, that kind of thing. But the term also covers just enhancing traditional control methods too.
Okay.
But the real core drive, now in the 21st century for intelligent control is balancing those two things we mentioned. Maximizing performance, what the paper calls smart, and guaranteeing safety, which is just non-negotiable for real-world systems.
Right, non-negotiable. So the million-dollar question is, how do you build controllers that hit both targets, optimal smartness and provable safety?
And the paper argues that real intelligence, true intelligence in a control system isn't one or the other. It's the synthesis. It's that AI adaptability, but guided and, crucially, constrained by a really robust safeguard mechanism.
Okay, safeguard. That sounds key.
It is, and this leads us nicely into something called Unfalsified Control theory, UC, proposed back in '97 by Safonov and Tsao. And it was pretty revolutionary at the time. The amazing part was it didn't need a traditional model of the plant, the system being controlled.
No model. How did it work then?
It just used measured data, the inputs going into the system, the outputs coming out, that's it. And based only on that, it could make decisions. It could even stabilize systems that were unstable and totally unknown beforehand.
Wow. That sounds incredibly powerful already.
Yeah.
So what was the catch? Why wasn't that the final answer?
The catch. Well, the big hurdle, and this was identified later, around 2007 by Engel, Temetsky, and Wonghong, actually, was that the original UC framework could only figure out the performance of the one single controller that was currently running the system.
Just the one that's active.
Exactly. It couldn't tell you how any other potential controllers might perform if you swap them in. There was this tricky mathematical issue, a pole zero cancellation blind spot, basically.
A blind spot. So the AI couldn't explore.
Precisely. It made it impossible for an AI optimizer to safely explore a whole range of alternative control strategies or policies without the very real risk of destabilizing the actual physical system. You'd have to connect a new controller to find out if it was bad, which is exactly what you don't want to do.
Okay, so that's a major limitation.
Yeah.
You can't safely let the AI learn and try new things. But here's where our source material gets really interesting, right? Because this research claims to solve that exact problem.
It does, exactly. It introduces this new methodology, and it's based on creating what they call an artificial error signal.
An artificial error signal. Okay, what does that do?
This is the crucial innovation. It lets the system, lets the AI, evaluate the performance of a whole set of potential candidate controllers, maybe hundreds, maybe thousands, all in real time.
A whole set. But wait, you said the old way couldn't do that safely.
Right. And here's the key difference. It evaluates them without ever connecting those untested controllers to the physical system, not even for a millisecond.
Ah, okay. So it's like a simulation, but based on real data.
Sort of. It creates what the paper calls a data-driven safeguard system. It uses the real-time data from the one safe controller that is running, but uses it cleverly to predict how all the others would behave.
So this data-driven safeguard, It's like building a virtual sandbox for the AI. Is that the idea? What do they call this sandbox?
We call it a fictitious fitness landscape.
Fictitious fitness landscape. I like that.
Yeah, it's a good term. Think of it exactly like that. A safe, virtual testbed. The AI optimizer, they use something called an evolution strategy, or ES, in the paper, can explore this landscape, tweak the controller settings, find the best combination, all without any risk whatsoever to the actual physical system.
A safe playground. Okay, the paper gives an example, right? I think walking through that makes it much clearer.
Yes, they did. It's a good one. They used a standard third-order stable plant model. Think of it like a common industrial process. PS equals 6 over, S plus 1, S plus 2, S plus 3, and a standard PI controller. Pretty common setup.
Okay. And they first figured out what the absolute best performance should be, like a benchmark.
Exactly. They used established math, the Ruth Hurwitz criterion, to know that one key controller setting, the proportional gain KP, had to be between 0 and 10 just for the system to be stable. Then they defined a cost function, basically, a measure of how well the controller is doing.
Lower cost is better.
Lower cost is better, yes. Using their evolution strategy with full knowledge of the plant model, they found the ideal optimized controller. Turned out to be KP around 3.42 and another parameter, TNN, around 3.64. That took 18 generations of the ES to find. So that's the gold standard. Perfect knowledge gives you this result.
Got it, the theoretical best. Now the big question. How did their new safeguard system, the one working only from data in the fictitious landscape, measure up? Did it get close?
That's the test. So using their artificial cost function, the system successfully computed that fictitious landscape. Then they let the evolution strategy loose on that landscape. And importantly, they started it with a really diverse set of 16 controllers. Some were deliberately unstable KP values way outside the safe zone, like Mediciv 5 or 15, teen values all over the place too, 1 to 50.
So starting from potentially dangerous settings.
Right. And after 20 generations exploring this safe fictitious landscape, it converged. It found what they call the fictitious optimized controller. The values were KP approximately 2.94 and TN around 3.24.
Okay, so 2.94 versus the ideal 3.42 for KP and 3.24 versus 3.64 for TN. That's actually pretty close.
It's very close, especially considering it was derived purely from data within the safeguard, with zero risk to the actual plant. It never had to try those dangerous initial controllers on the real system.
That really validates the approach. It found a near-optimal, safe controller just by looking at the data through this clever artificial order signal.
Exactly. It proves the concept. For context, they also mentioned using a standard tool, MATLAB's PidTune function, on the known plant model. That gave KP of 1.26 and Han of 1.51. Also stable and decent, but the safeguard method actually got closer to the true optimum found by the ES with full knowledge.
Wow, okay. So the ability to predict how controllers will perform without actually running them on the real system, just using measured data.
Yeah.
That's the core breakthrough here.
That is absolutely the core.
It all sounds incredibly powerful. But my next thought is, how is this even computationally possible, evaluating potentially thousands of controllers in real time? That sounds like it would need a supercomputer.
Good question. And this brings us to maybe the most elegant part of the whole thing. The paper calls it the intelligence of avoiding the inverse.
Avoiding the inverse, okay.
So the heart of the method, the calculation needed to estimate the performance of all those candidate controllers, involves a mathematical process. Technically, it's estimating something called the sensitivity function for each controller using deconvolution.
Okay, deconvolution. That sounds complex. Can you simplify that a bit?
Yeah, let's break it down. Fundamentally, this deconvolution step boils down to solving a big system of linear equations. You can write it like axb.
Okay, xb, classic math problem.
Right. Here, x is the thing we want to find. It represents the sensitivity function coefficients for a candidate controller. B is something we know it's derived from that computed fictitious error signal we talked about. And A is a special kind of matrix built from the reference signal, also known. It's called a lower triangular Toeplitz matrix.
Lower triangular Toeplitz. Okay, sounds specific.
It's very specific. It has a particular repeating structure. Now, the avoiding the inverse part comes in how you solve for x.
How would you normally solve x equals b?
Well, the sort of naive textbook way might be to calculate the inverse of matrix A. Then x just equals A inverse times B.
Simple formula.
Right, find the inverse, multiply by B, done.
But for the kinds of large matrices you get when dealing with real-time data streams, long sequences, calculating that inverse directly is, as the paper says, computational prohibitive.
Yeah.
It just takes way too long. And it can also be numerically unstable, meaning prone to errors. It wouldn't be practical for real-time, use at all.
Okay, so direct inversion is out. Too slow, too risky. So what's the elegant solution? How do they avoid it?
The elegance is because matrix A has that special lower triangular topeless structure. That specific structure allows the system X equals B to be solved with extreme efficiency using a different technique. It's called forward substitution.
Forward substitution. How does that work? Instead of one massive inverse calculation, it's an iterative, step-by-step process. You can calculate the first element of x, let's say psi 0, directly from the first equation. Then you use that value in the second equation to calculate the next element, psi 1. Then use those two to find psi 2, and so on. You just work your way down.
Ah, okay. So you solve it piece by piece using the previous results.
Exactly. And because of the matrix structure, it's incredibly fast. The paper notes it has very low computational complexity. It makes that whole deconvolution process, estimating the performance of all those controllers, really quick and efficient, perfect for real time.
So the structure of the problem itself provides the key to solving it efficiently. That's clever.
Very clever. It's about recognizing and exploiting that structure.
You know, this idea, avoiding a massive direct calculation, because the underlying structure allows for a smarter iterative approach. That sounds familiar, like it might apply elsewhere.
You are absolutely right. And the source material makes this exact connection, actually. A really great comparison to Google's PageRank algorithm.
PageRank, how Google ranks websites, how does that connect?
Well, at its core, PageRank is also about solving a gigantic system of linear equations, absolutely enormous. The matrix, in that case, represents all the links between all the pages on the entire web.
Okay, I can see how finding the inverse of that matrix would be problematic.
Problematic is an understatement. It's practically impossible, computationally unthinkable.
So Google doesn't calculate the inverse of the internet matrix. Shocker. What do they do?
Exactly. They use a similar philosophy. Google employs an efficient iterative method called power iteration to find the PageRank solution, the principal eigenvector of that massive matrix.
Power iteration. Okay.
The underlying principle, as the source highlights, is the same. When faced with large-scale linear equation systems in the real world, efficient iterative methods are always superior to direct inverse computation.
So this safeguard method, using forward substitution, and PageRank using power iteration, they're both examples of intelligently tackling these huge AXB problems by avoiding the brute force inverse.
Precisely. It's a powerful concept that shows up in different fields, finding that efficient, practical way to get the answer without getting bogged down by the sheer scale.
That makes a lot of sense. It's clear how powerful this is academically, but let's bring it back to the practical side. Why should our listeners really care about this computational efficiency, this avoiding the inverse? How does it impact the real world?
Well, that speed, that computational efficiency, that practical feasibility, that's actually what makes the entire safeguard concept viable in the real world.
Ah, okay. It's not just a nice to have, it's essential.
Absolutely essential. The ability to rapidly assess, hundreds, maybe thousands of potential controller settings and build that fictitious fitness landscape in real time, that's crucial. If it took minutes or hours, it wouldn't work for controlling a dynamic system. It has to be fast.
So even though the paper showed results in a simulation, the engine underneath, this efficient calculation, is ready for prime time. It's robust enough for actual physical systems.
That's what the source strongly suggests. It emphasizes that the inherent efficiency and the low complexity make it perfectly suited for deployment on physical hardware with limited processing power. They specifically mention things like microcontrollers or even a Raspberry Pi.
A Raspberry Pi. Seriously, you could run this safeguard on that.
That's the implication. This isn't some theoretical thing needing a server farm. It's designed to be a robust, computationally feasible, and practical blueprint. It's meant to be deployable.
That really changes things. It means AI could genuinely learn and optimize control systems out in the world, safely, without ever risking the stability of the power grid, or the chemical plant, or the autonomous vehicle.
Yes. That's the potential paradigm shift here. Building trust, allowing AI to improve systems continuously, but with guardrails that are mathematically sound and computationally cheap.
That's huge.
It really is.
Yeah.
And the paper, concludes by looking ahead. Immediate next steps are experimental validation on exactly that kind of low-cost hardware, Arduino, Raspberry Pi.
Putting it to the test in the real world.
Exactly. And then looking further out, the goal is to scale this safeguard architecture up to handle the really complex, high-dimensional policy spaces you find in modern reinforcement learning. The ultimate aim, developing certified control systems for safety-critical autonomous applications.
Certified safe AI control.
That's the vision. This approach provides a clear pathway towards that goal. Truly intelligent and autonomous control, but built on a foundation of verifiable safety.
So wrapping this up, what we've really dug into today isn't just, a clever bit of engineering. It feels more fundamental.
I agree.
It's like a foundational step towards AI systems that can learn, adapt, get smarter over time, but without ever putting critical infrastructure or even lives at risk. It's using math elegantly to solve a really practical, pressing problem.
That sums it up well. This method lets us safely weave AI learning right into the control loop. It provides that unfalsifiable, data-driven safety net. It genuinely lets an AI explore and optimize without needing a perfect model beforehand and without risky real-world trials.
So think about this for a moment. Consider all the systems you interact with or rely on. Your car's brakes, maybe adaptive cruise control, the grid delivering power to your home, industrial processes making things you use.
Critical systems everywhere.
If AI can genuinely learn and fine-tune its control in a totally safe virtual space, testing thousands of ideas a second, before its best solution ever touches the real hardware, what does that unlock? What new levels of efficiency, responsiveness, and intelligence become possible? And, maybe most importantly, become trustworthy?
That's a really exciting question for the future.
That is all the time we have for this deep dive. We really hope you feel a bit more informed and maybe a lot more curious about where AI and control systems are heading.
I hope it was useful.
Until next time, keep digging deeper.